Hi, good evening, everyone, and once again, a pleasant welcome to our APET Mechanical Division Technical Seminar. This evening, we will be looking at a very interesting presentation by Mr. Rishi Jawahir, and he will be presenting Diagnosing Bearing Defects Utilizing Vibration Analysis. Now, a little about Engineer Jawahir. He is one of the leading authorities locally in Trinidad and Tobago in the field of mechanical engineering, with extensive experience in vibration analysis and maintenance strategies. His work has significantly contributed to enhancing the reliability and performance of industrial machinery within the region. I think we can say that any contribution to these fields, especially mechanical engineering, is always welcome. And once again, we are very appreciative to have Engineer Jawa here with us today to present his topic on the diagnosis of bearing defects utilizing vibration analysis. So I will give Engineer Jawa here the floor. Rishi, it's all yours, and you can
Hi.
start sharing.
Hi, good evening. So thanks very much for the introduction. Is everyone seeing my screen or the presentation?
Anok, can you please reshare?
Yeah, I think it fell back down. Okay, how about now?
Great.
Yeah, I'm seeing it now. Yeah.
Okay, all right, that's great. All right, so good evening, good afternoon, whichever part of the world are you joining us, it was good morning. So thanks for taking the time to join us this afternoon. So as you mentioned, we have this short presentation this evening, diagnosing bearing defects utilizing vibration analysis, and it's specifically around rolling element bearings. So we're just here to share some knowledge, some experiences that I may have out in the industry, diagnosing bearings, and hope everyone can learn. There's some at least some housekeeping rules, at least for the duration of the presentation. If you have any questions, at least you could type it into the Q&A section. All right, and hopefully after the presentation, we have some time allotted for Q&A, and I'll go through your questions and try my best to answer as much as I can. And so let's get started. Right. Right. So I always like to start my presentations, any discussion, any meeting I have with safety, because safety is of utmost priority, especially most of us in the mechanical industry, engineering, whatever industry you are in. There are safety risks and hazards involved, especially with rotating equipment. So those who are involved in the maintenance, diagnostics of rotating equipment, there are a lot of hazards present, especially direct line of fire. So, especially in this area of condition monitoring, vibration analysis, where you are routinely or in a close proximity to rotating equipment, there are the risks of line of fire. So, what we recommend any job you're doing, try to stand clear of coupling areas, line of fire, especially on the startup of any rotating equipment, especially after any recent maintenance activities, any intervention into the equipment. Always stand clear of the line of fire. Rotating components, especially with those who are in coveralls, always have the sleeves button up, your gloves tightly placed, no loose clothing. All right, especially with equipment, there are high noise levels. So ensure you have the appropriate PP, whether it's earplugs, earmuffs, or double hearing protection. Also, hot services if you're around steam turbines, gas turbines, hot process conditions, process condensate pumps, any kind of hot process area. Ensure you have the appropriate gloves around hot services, right? Right, so just introducing this topic we have here on bearings. So bearings are very important, and most of us use it in our daily basis, I can say. All right, from our home appliances, we may have maybe a blender. We have some appliances. Our kids may have bicycles. They ride bicycles, so you want to ensure that the bicycles are operating effectively. To the airplanes we go, so we might go on a vacation. There may be airplanes, so I didn't show the bearings on those airplanes are good also. Medical equipment, and in our industry, industrial equipment, motors, pumps, turbines, compressors, they have rolling element bearings, right? Now, why it is important to have high reliability? Because reliability and safety goes hand in hand. So when there is a reliability issue or an equipment with a known, could say bearing fault, it also poses a safety issue onto the plant. So you don't want to have your operators, your technicians, those doing your condition monitoring, your testing. You don't want them for any lengthy period of time around rotating equipment that has known defects or vibration issues, and also for the availability for production. So you may have your production process, whether you may making, I don't know, manufacturing process, soft drink, you may bottling, canned soft drinks, you may making ammonia, LNG. You want to ensure you have high reliability of those operations, right? Now, through the whole, could say, value chain of rolling element bearings, there are introductions of some type of defects along that value chain. All right, from the application, from the installation to the maintenance and lubrication. So we have to ensure at each part of this value chain, there's high reliability, there's high precaution that is being taken from the supply, from the application, because if we select the wrong bearing for the application, we would not have a high life or high reliability of the bearing. Thus, we may have early or premature failure. From the insulation, I think most of us have seen in industry where people use the wrong insulation practices. They may pong a bearing into place. They may have the wrong tolerances, the wrong clearances, and that puts undue amount of load or stress onto the bearing, which results in premature failure, which affects our production, which affects our safety. Also, in the maintenance and lubrication, we may have the wrong maintenance strategy. We may be using the wrong type of lubricant or the wrong lubrication schedule, and that also affects the reliability and operation of our bearings, right? Now, so that's a basic introduction and types of bearings. Some of us may be aware, some of us might not know, but there are many types of bearings, but one of the main or most popular use in industry is the ball bearing. I sure most of us have seen one of these or heard of it. Or when you're playing marble pitch long time, somebody, father or brother might have had of old ball bearing, and got a slug from the bearing. So that would have been a ball from the ball bearing, right? So the ball bearing is mostly used because one of its ease to manufacture. It's one of the relatively smaller or most effective, could say cost effective bearing to be used. They are what we call the rolling elements, and these provide a contact surface from the stationary part, could say, to the rolling part of the equipment. And this contact area what supports the load of the equipment. So, as for example, you may have a motor, you may have a pump. That pump or that motor has what known as a rotor, and that has a weight. And these bearings provide numerous functions. One main function is supporting the weight of those rotors, also to provide a ease of friction, so there's a smooth rotation. So these provide support in the load of these rotors. The thing with ball bearings, they are limited in their load carrying capacity, and they are mostly limited in terms of the load they can carry in a radial direction because of the contact with the ball and its stationary part, right? Roller bearings, so unlike the previous brother system of the ball bearing, these rolling elements are like a cylinder. So if I picture, I may have a cylinder. Most of us know what a cylindrical shape would be. So these are commonly called cylindrical roller element bearings, or some people will say cylindrical bearings. And these provide a wider contact or longer contact area between the rolling part and also the stationary part. So it gives it a higher load carrying capacity. All right. Also to provide um, more load support, more loads in terms of larger rotors. All right. Also suited in a radial direction. And one of the limitation with this in terms of It's not well suited for misalignment applications, right? Now, there are many variations of different types of bearings, and one is the spherical rolling element bearing. And this has an element that's shaped kind of more of an elliptical shape of its element. Now, what this does, it provides effective load current capacity both in its radial and axial directions. So it's more suited for very high or rugged applications, durable applications, applications where we have load in both directions, where we have a higher or where we need a higher tolerance for misalignment. So we may choose this type of bearing. There's also a smaller type of bearing known as a needle bearing, which is a variant of the cylindrical bearing, but has smaller or narrower type of cylindrical elements. More used where we have limited space available and also limited in its load carrying capacity. And they have many variations of these other types. They are tapered, roller, tapered, needle, and it's just a combination of terms of your application. So it comes back to the first point we had in the application of the bearing. So you have to ensure one, the correct application for what you need. If it's a load you're carrying, ensure you have the correct bearing for this application. All right. Right, so this is a basic overview of the different types of bearing mostly used in industry. We have ball bearings, cylindrical roller bearings, spherical, tapered bearings. This guideline of sometimes is what you know as a bearing number. So sometimes you may hear or see in industry, you may see a 6306 bearing. The first number or first part of the bearing, there's a specific number or letter assigned to that bearing to help you guide what type of bearing it is. So typically number 6 guides you to ball bearings. Um, Typically number 2 guides you to spherical bearings. So it's used to kind of guide the user in terms of the correct bearing for its application. Right, so kind of coming to diagnosing the bearings. All right, so I always teach all my students, especially with rule and element bearings, it's important to remember the number 4. All right, FOUR, the number 4. So if anything stick with you in this presentation, remember the number 4. Rule and bearings has 4 major components. All right, we'll go through each of these. They have 4 defect frequencies, and they also have 4 stages of failures. All right. So we'll get each one of these individually, but it helps you to guide in terms of diagnosing the correct defect of the bearing and also diagnose what stage of failure the bearing is at. So just simply remember the number 4, right? So the major parts of the bearing, we have the inner race, as you could see here in the diagram. The inner race is what's normally our shaft of the rotor. If it's a motor shaft, a pump shaft, it's actually fit into the side of this component. We have the outer race, which typically fits inside of the housing. If it's a motor housing, bearing housing, typically inside here, and these are sometimes or most of the times what they call interference fit. So sometimes they may have to be heated, the bearing housing, or cooled to ensure there's a tight tolerance fit of the bearing into the housing or the shaft into the inner race. We have the rolling element, and we just went through different types of rolling elements. They are ball bearings, spherical bearings, cylindrical bearings, tapered bearings. So this is what is known as a rolling element. And then there's a cage, what keeps or maintains the elements in place. And each one of these components generates its own frequency, right? So that's why we remember the number 4. So as we get kind of more into vibration, that's kind of basic. This is just a very basic overview. What is vibration? So those who are not familiar with vibration, and basically what vibration is measuring the response of any mechanical system from an applied force, right? So simple example, we may have a motor, we may apply a load, and most of the times it's the running speed of the equipment, and we're actually measuring the response of that input, right? And that response we are measuring is what is known as vibration, right? There are main or 3 main characteristics of vibration, what we use in the vibration world. we have frequency, we have amplitude, and then there is phase, right? So at least for the context of this presentation, we'll just be focused on the first two, which is frequency and amplitude. I believe in our next presentation, we could do something on phase, right? Now, frequency simply tells us what is causing a problem, all right? Simply put it in terms of practical example, we may have a motor or pump. The frequency tells us which part of the component or which part of the bearing, all right? Remember, we talk about the four parts of the bearing, inner race, outer race, the elements and the cage. So frequency tells us or guide us what component is actually causing a failure. All right. And frequency, most of us know, will actually be measured in certain units. All right. These are measured in hertz, cycles per second, or cycles per minute, and also in vibration terms, what is known as orders. And we'll get to orders coming up in a presentation. Simple example, we all have our electrical outlets. Please don't put anything in the electrical outlets, but in the electrical outlets, you will be measuring or you will receive electricity, for example, at 60 hertz or 50 hertz, wherever it may be in part of the world. That's one measure of frequency, that's line frequency. We may have cycles per minute or in orders, right? Right, the other main characteristic of vibration is amplitude. So amplitude tells us how severe a problem is. So we spoke about frequency. Frequency tells us what is causing a problem, and then amplitude tells us how severe a problem is, right? So there may be bearing frequencies, there may be other frequencies happening in your rotating equipment, but frequency guides you what is causing a problem, and also amplitude tells you how severe a problem is. And when it comes to maintenance strategy, um, yes, all equipment may have defects, they may have faults happening, but the severity will guide you. Okay, well, I could plan my maintenance for maybe a 3 months or 4 months period, or based on the amplitude or severity, it's of a high amplitude, high severity. I need to take some immediate action. So the amplitude guides you along those that guideline. And we can measure amplitude in three main, I could say, units. Displacement is one. So displacement is actually actual measurement of the movement of the equipment or whatever we're measuring. Displacement can be measured, most of us are familiar with mils or in microns, and this can be measured in units of peak to peak, what is the total distance actually traveled. All right. One other unit of measurement for this vibration is known as velocity, and velocity is the rate of change of displacement with time. All right. Velocity is measured in inches per second or millimeters per second. All right. This can be represented known as peak velocity or RMS velocity. And then there's also acceleration. So acceleration is a rate of change of velocity with time. All right. Um, Acceleration can be measured in G's, and we'll see that coming up to the presentation here. But in terms of vibration analysis, how I like to put the example, we all have, I think most of us may have a vehicle or have driven a vehicle before. One classic example, be at the traffic light, the light is at red. When the light turns green, I think we all like to march down hard on the X, but as we march down on the accelerator, or the X pedal, let me call it, the vehicle attains a certain acceleration, all right? So the vehicle will accelerate, and based on that acceleration, the car obtains a certain velocity or a certain speed, how much kilometers per hour you may go in. And then after that speed, now you will travel a certain distance, which is known as displacement, right? So with rotating equipment during startup or during normal rotation, there will be acceleration, there will be velocity, and there will be displacement. So it all depends on your measurements, and we'll go to that shortly, which units you're actually measuring from the equipment, right? Right, so typically what we do in vibration analysis, we measure the response, all right? So typically what we have what is known as an accelerometer, and we'll have this placed on our equipment or the bearing housing, and actually measures the raw signal or the vibration of the equipment. and is measured onto vibration equipment or a vibration analyzer, and it gives you what is known as a time waveform, right? This is actually how the vibration is varying with time. Now, there are certain mathematicians, and this was developed long ago, that they said or they mentioned no matter how complex or how many vibrations, how many frequencies you may have in equipment, could be how complex it is, it could simply be broken down into individual frequencies. And that is the simplest explanation of Fourier transform. So some of us might be familiar with Fourier. There is a program that can be used to break down these time or the time waveform into its individual frequencies, right? And there's the invention of the fast Fourier transform, which makes it actually faster. And these can be done in matters of seconds or milliseconds, right? So no matter how complex the machine may be behaving, once you do a fast Fourier transform and breaks down the time waveform into what is known as a vibration spectrum. And this gives us the individual frequencies occurring in an equipment, right? Right. So I mentioned before to you, in diagnosing bearing, always remember the number 4, right? So we talk about the 4 main parts of the bearings, which is the inner race, outer race, and also the balls and the cage, right? And then there are 4 stages of bearing failure. Right, so the 4 main frequencies being developed by the bearings. The first one, what is known as a ball pass frequency of the inner race. Right, this is just a generic, generalized equation for calculating there. If you have on the internet, on Google, or there are many softwares out there available. Once you input that bearing number we saw from the beginning of your presentation, if it's a 6 bearing, the number n, whatever bearing number you may have, and you input that number, it will give you automatically the bearing defect frequencies, right? So sometimes you don't need to calculate this, but I'm just trying to show you the relationship it has with each one of these, the inner race. The defect frequency of the outer race is known as the ball pass frequency of the outer race. For the actual elements itself, which is a ball or a roller, it's known as a ball spin frequency. And then there's known as what is known as a fundamental train frequency or the defect frequency of the cage itself, right? So there are many software available, commercial software, free software available. You could Google right now and see it comes up free. Just input the bearing number and gives you all these defect frequencies, right? So we talk about the 4 main parts of the bearing. Then we just spoke about the 4 defect frequencies. So I'm going to speak about the 4 stages of bearing failure. And this also is very important because it kind of guides your maintenance strategy. How far or at which stage you are in a bearing failure determines, okay, maybe you need to place a work order immediately, or you could place a work order for within the next 4 to 6 months. And this guides your maintenance strategy, right? Now, the first stage of bearing wear or bearing failure, it's very early in the failure of the bearing. And this is what is known as micro vibrations, as you could say, because it actually involves like subsurface wear or wear due to degrading lubrication. So what it means then that is actually friction occurring between the rolling parts of the bearing. And those who study vibrations, that friction actually creates or generates very high frequencies, which is known as ultrasonic frequencies, right? Now, as you can see, there's a small diagram on top, which is your vibration spectrum, and shows you here exactly what a stage 1 bearing failure may look like. It indicates very high energy or high activity in the what we call very high frequency range, all right, which is typically above 20 to 25 kilohertz, which is 20 to 25,000 hertz. All right, sometimes we require special accelerometers or special techniques. All right, we'll get into those techniques, diagnosing or picking up early or stage 1 bearing failures. And you could see in the image below that where you have uneven surfaces, and this is at the microscopic level of the two surfaces, if it's between the outer race and the balls or the inner race and the balls. This is due because of there's no ideal perfect surface out there. And that's why lubrication is important to keep an even film across rotating components, right? Now, this frictional vibration, as you mentioned, is very high frequencies, above 20 to 25 kilohertz. And we need specialized techniques to pick up on these and also identify these effects, right? Now, typical very high frequencies, so it's in VHFD, very high frequency detection techniques. And these are commercial patented technologies out there in industry that has been using, I think, for the past decade or two. All right. Peak View is one from Emerson. There's Shock Pulse, there's SPM Spike, Steve, and there are many other methods out there by different manufacturers, different vendors, and they all work perfect. They all work fine. It's just on you to understand how to use it and the settings and stuff like that, right? Then actually moving now to stage two, right? So at stage two, we develop slight surface wear, or there may still be subsurface wear, maybe more degradation of lubrication film or an increase in frictional vibration. What we may start to see, as you can see here in the vibration spectrum, is an increase in amplitude of this VHFD, or this very high frequency. You may start to see an increase in trend. So it comes back to maintenance now in terms of your maintenance strategy, because sometimes condition monitoring may be done on a monthly basis. Some companies have it on maybe every 6 months or every quarter. And especially for your most critical equipment, you don't want to have condition monitoring being done every 6 months or every quarter, right? At least minimum to start is on a monthly basis. You may have vibration data being collected on equipment. And as defects start to increase, you have what they call bad actors. And we want to increase the vibration monitoring frequency from maybe monthly to maybe or every 2 weeks, or then come back down to every 1 week, right? But as you have trended data and you start seeing an increasing trend in these high frequency detections, it gives you, okay, there's some, or this fault is developing further and further and further. All right, there may be more friction happening, the subsurface wear may be happening more, or there may be an inception of surface wear or surface cracks, stuff like that, right? So we still use these techniques, the very high frequency techniques. We still use them, we still employ them, all right, which is a peak view, the shock pulse. We still use these techniques, and you could also use something known as enveloping or demodulation. We will get to that shortly. But for analysis purposes, the velocity, we mentioned velocity before, will that be effective in kind of diagnosing these types of faults, right? So it's good to know the stage of failure you are in and the type of technique or units to look at the vibration. We talk about acceleration, we spoke about velocity, we spoke about displacement. So for very higher frequency ranges, we'll typically look in acceleration. And as bearing starts to wear, there's more increase in vibration, we'll typically start to see activity in the velocity region, right? Right, so getting to stage three, and stage three is typically where we want to plan our maintenance activities, all right? Because sometimes I've seen people diagnose bearing at a stage one failure very early. They may see an increase or start to see high frequency detection and start, okay, well, yeah, peak view is high, shock pulse is high, and start trying to take down the bearing. And when they do pull down the bearing, take down the bearing, there's nothing to be seen. All right, bearing looks good, bearing looks healthy, bearing looks perfect. But in true, at a microscopic level, the bearing is not good. All right, but still, in terms of proper planning, proper scheduling, you may try or want to have a maintenance intervention at this point at stage three. At this stage, you may have visible wear. So visible wear with the naked eye as compared to microscopic wear or subsurface wear. All right, there will be an increase in high frequency range. So we're kind of moving down, as you can see from the spectrum here. We're moving away from that very high frequency range. So we're moving away from that 20 to 25 kilohertz range. We're coming down now to maybe within a 5 kilohertz range, right? What is known as high frequency detection, or HFD. And we may start to see an increase in that region. And typically, we may start to see defect frequencies in the velocity region, right? So we mentioned, if you remember, the four defect frequencies: the inner race defect, outer race defect, the ball spin, and also the cage. We will start to see these frequencies also with harmonics, all right, which are multiple integers of these frequencies starting to occur in the velocity region, which is like typically in a lower frequency range. So sometimes maybe within 1,000, or maybe like within 10 hertz up to maybe like a 500 hertz, 1,000 hertz. You may see this in the velocity region. And we could also start using our time waveform. So we talk about a time waveform. We could use time waveform is a very good technique to be used also in vibration analysis, to look at for impacting and sometimes modulation, right? Now, at this point in time, if there's no intervention into the bearing, there is the possibility of failure happening rapidly, all right? And coming to the latter stage, or the last stage of bearing wear, excuse what is known as stage 4. All right, at this point, there's significant bearing damage happening, something known as secondary damage, where one component fails and causes secondary damage on the other parts. So in the beginning, you could start it off with maybe there's an outer race effect, but because it was neglected, there was no intervention, the fault developed so significant that it causes secondary damage to other components, causing a total failure of the bearing. All right. At this stage, there is no such of high frequency or HFD activity. It comes down to the lower frequency or mid frequency range, and we start seeing what is known as noise. Right? There's randomness. There's nothing periodic about this activity. We may start seeing something known as mechanical looseness, maybe high 1x with harmonics. So sometimes you may test an equipment, the bearing might be at this latter stage of failure. And some people miss it because they are looking specifically for the bearing effect frequencies that we mentioned before. And because they are not seeing the bearing effect frequencies, they may say, okay, well, there's noise in the spectrum, there's randomness. So the bearing is no issues with the bearing, right? So sometime at this point in time, the bearing may be past all those stages of failure and maybe in the latter stages of failure where there's high mechanical looseness or high noise or random vibration. And at this point, there may be bearing failure that's very close, right? Right, so talk about coming to testing now. So we talk about types of bearing, components of bearing, stages of bearing failure, where, and typically what we will need to actually conduct a vibration measurement and diagnose bearings, right? So typically we use what known as industrial accelerometers. These are like general purpose accels. Typically 100 millivolt per G sensitivity is required. These sensors are connected via cable. Now with technology, they are wireless vibration. So maybe our next presentation, we could talk about wireless vibration. But typically this is wired to a data collector. So there are many different brands out there. Some people have different brands, different preferences. All right, so this is wired to a portable data collector. And this actually captures the vibration data during a route or during routine maintenance or data collection, which stores the vibration data onto the instrument. So the instrument has the ability to do the FFT on site, the fast Fourier transform. So you could do a spectrum analysis on site to diagnose the bearing. And the same defect frequencies, some instruments are able to display those defect frequencies on site. So right there on the site, you'll be able to diagnose if there's a decisive bearing defect or not. Sometimes we require a vibration software. So with this software, you could do post-processing, you could do spectrum analysis, you could do your time waveform, you could do circular plots. So it all depends on what is available to you. But typically, this is what you will need to actually collect vibration data and perform spectral analysis to confirm bearing effects, right? So some of the techniques we mentioned, some of the techniques or technologies used, VHFD, very high frequency detection. All right, HFD, high frequency detection. So some of the technologies, especially for early parts of bearing wear, we can use ultrasound. All right, we could use ultrasound analysis for detection. So we mentioned before that early stages of bearing wear, stage 1 happens in a 20 to 25 kilohertz range, and that is really the ultrasonic range. All right. The other technology is PeakView and PeakView Plus. PeakView Plus kind of goes a bit step further and actually differentiating now the type of wear or defect you have. So whether the bearing defect is more related to a lubrication issue or it's more related to actual mechanical or bearing defect, right? So this will help you know, okay, do I need to grease my bearing? Do I need to flush my oil? Or do I need to have a live ultrasonic greasing? This kind of helps you guide you on that guideline. There's envelope demodulation, time waveform can be used, all right, which is a circular plot. And there's autocorrelation, which is a time waveform method to kind of diagnose if there's any type of bearing failures, right? Right, so kind of basically explaining what is enveloping demodulation. And this is the principle of most of the vibration equipment out there to diagnose bearing effects, especially those high frequency range types of defects. So how I like to put the analogy, most of us here in Trinidad are familiar with cricket, all right? So you may go, or any kind of sporting event, you may go to a stadium where there's a lot of noise. A lot of noise actually happening there. But you know, in the middle of all that noise, you may trying to hear very small effect or very small ping will be very difficult for you, right? Similar with these bearings here now, these rotating components may have a very small effect. So every rotation is a ping, ping, every rotation is a ping. But because it's so small, so minute, it's being drowned out by the normal operations of the equipment. So you have this running speed, it could be a pump, it could be a motor. These are a bit more of high amplitude and higher noise, but it drown out the bearing frequencies, right? So what it has to be done, it has to go through this type of a signal processing technique to kind of filter out the unwanted vibration. So it gives you now the actual bearing effect frequencies for proper diagnostics, right? So one of the first step it goes through is through a filtering process. So it kind of goes through a high pass filter. So it kind of filters out all those type of other frequencies you don't want from the machine, the noise. You only want what is concerned with the bearing, the high defect frequencies, right? It actually goes through a rectified circuit, so or enveloping, so it kind of gives you the actual shape of the frequency or the modulation you're looking at now. And again, it's passed through another filtering process. And also now through that second part filtering process, it gives you the envelope or gives the actual defect frequencies you're looking at. And now it's passed through again the fast Fourier transform and it gives you the bearing defect frequencies, right? This is a simple explanation of amplitude demodulation or enveloping. Some people may have it. Each technology has a different spin on it, but basically this is what it entails. It's a signal processing technique. It's a filtering technique, uses high filter, low pass filters to filter out the unwanted vibration and gives you actually what the bearing effect frequencies are for you to perform your diagnostics, right? Right, so kind of getting into the analysis. So we talk about the vibration spectrum. And bearing effect frequencies are what are known as non-integer or non-synchronous vibrations, right? They do not occur at multiple integers or whole integers of your running speed. So this simple example, you may have a motor or pump running at a certain speed. That speed is known as its fundamental frequency, or what is known as a 1x frequency, which is in terms of orders. Simple explanation. And then there are multiples of that. There'll be 1, 2, 3, 4, 5, right? In the vibration spectrum, we will look for synchronous vibrations. We look for what is known as non-synchronous or non-integer vibrations. And then we look for known as subsynchronous vibrations, which is below or to the left-hand side of the 1x, right? So typically, bearing effect frequencies are non-integer or non-synchronous vibrations. So we do something called order normalization, where we put our vibration spectrum in terms of orders, and any spikes or any frequencies we see that's not a whole number, that's not a 1, a 2, or 3, somewhere in between these frequencies are what are known as defect or bearing effect frequencies. All right, they are non-integer. If they are subharmonic, sometimes what is less than 1x, and these are element bearings, not general bearings, it can be associated with the defect frequencies, right? So I mentioned the inner race, outer race the ball or element, and the train. And there's a reason why I put it in this logical or hierarchy, because the ball pass frequency of the inner race is the highest frequency of all of these, of the four. So typically this will be within a higher range of the others. BPFO is second, the ball spin is third, and then the train, the last one, is a sub-synchronous frequency, right? So what it means, so that if you're seeing a frequency which is less than a 1x, and it's a non-integer, well, it will be a non-integer, it typically could be a train frequency happening there, right? Right. So back to the analysis. So the inner race, the effect frequencies, they generate what is known as sidebands. So these are modulating frequencies. They generate sidebands around the inner race space at the 1x. So what it means now, that every revolution of the shaft, or every revolution of whatever rotor is, that shaft speed actually modulates or increases, decreases the amplitude of the inner race effect. That gives you BPFI, or inner race effects, with sidebands of 1x. Typically, that is what you'll look for in a vibration spectrum. The ball spin effect frequencies, this also create the ball spin effect frequencies with sidebands of the cage or the train frequency. And we mentioned before that the train frequencies, that these are sub-synchronous or subharmonic frequencies, right? And sometimes it's not uncommon to see harmonics of these. We mentioned that they are 1x with harmonics. And what will happen also, there will be bearing effect frequencies with harmonics. Sometimes you might not see the primary frequency, but you'll see harmonics of it. And sometimes that does occur. Sometimes people might be doing vibration analysis and they may see a harmonic of bearing effect frequency and maybe neglect it. But really and truly, is that's how it's set up. You'll actually not see the fundamental, but the actual harmonic of it. Right. So common failure modes of bearings. So one major one is lubrication, poor lubrication. So from the onset, ensuring bearings are properly lubricated. Majority of the times when bearings are shipped or when they are held in stock or when they are held in spare, they are not properly lubricated. They're supplied with a thin film of bearing just to avoid any type of corrosion during shipment or handling. So actually when being sold, it has to be properly lubricated. Corrosion, as you mentioned before, sometimes our bearings have seals, right? And sometimes the seals are not good, they are defective and allows ingress of moisture, may allow ingress of process conditions, and this has corrosion. Excessive loading, so we mentioned before, ensure the proper loading of the bearings are happening. All right, fatigue, normal fatigue life of the bearing may happen. False brenneling, so sometimes what happens during shipment, you have a new motor or a new pump being shipped, but because of the vibration during shipment, all right, during the transportation, we know we have very good roads here in Trinidad. So anywhere in the world, so during that transportation, there may be shocks, there may be impacts that happening and actually causing some defect onto the bearing when actually it's just a shock or during the transportation happening. Sometimes you may have two equipment next to each other, one equipment running, the other one is standby. But because vibration is being transferred from one equipment that's running to the next one that's offline, it may cause false brenneling. There may be contamination. So we mentioned seals may be broken, process conditions, dirt, wear, or especially when dirt gets seen and the dirt mix with the lubricant and with the ball and the face, it actually cause indentation and cause wear. Loose or tight fits, so sometimes our clearances might not be good. This actually causes too much pre-stress or preload onto the bearings and cause higher fatigue onto the bearing and results in a shorter life. Also, electrical fluting. So what happens now, sometimes our bearings are not properly grounded and there may be an electrical short. The electricity or current will flow from the equipment, especially motors, right? And actually flow through the bearing to ground and actually causes what known as fluting, where you see actual indentations around the race of the bearing. And this is common, this actually happens a lot. And what has to be done is proper shaft grounding, also ensure there's no stray voltages, And there are shaft rings that can be installed to reduce those shaft voltages. There are insulated bearings that can be installed to reduce these electrical floatings, right? All right, so these are just some case studies, typically what vibration spectrum may look like when they are bearing defect frequencies. So this would have been a BPI ball pass defect of the inner race. So we'll see we have the actual defect frequencies and harmonics. All right, this was taken from a centrifugal pump, a center hung pump, driven by an AC induction motor, and this was an SKF 6306 bearing. This was actually low oil lubricated bearing. All right. Um, this here we actually have a ball spin effect frequency, a ball spin effect of an element bearing. This was a 6220 bearing, was actually grease lubricated. Here we actually had a cage, a fundamental train defect, and I could see here that it actually was a subharmonic defect frequency. This was on a AC induction motor at around 3500 RPM, right? Grease lubricated 6220 bearing. Right, so typically that is a very short presentation on diagnosing bearings. I do hope that the information shared was helpful. I mean, if there are any questions, please feel free to ask.
Hi, Rishi. Thanks for
Hi,
that insightful
good night.
presentation. Good night, Christopher.
Hi, good night.
Yeah, good night. So what I'll do, I would ask that anyone who have any questions, I don't think any questions was typed, but if anyone has any questions, you could use the hand raise icon, and you could raise your hand, and I will take the questions from there, or at least moderate for this time being on the Q&A session.
Okay.
So we just ask that if anybody have any questions, you could address them with Rishi right now.
Thanks,
If
Christopher.
Yeah, no problem, Rishi. If I'm not getting any questions, like I might have to play a little devil's advocate and and ask on behalf. uh, so anyone, right? Let me
Yeah, so somebody
see.
raise a hand here.
Right, April,
April?
go ahead.
Yes, good evening.
Good evening.
That was a very nice, informative presentation about bearings. I have a question about your presentation that relates to our previous presentation that we got, which was on the different types of maintenance. We had reactive maintenance, predictive maintenance, and prescriptive maintenance. It looks as though you're doing one of these types of maintenance here.
Yeah.
If I had to hazard a guess, I would think it is predictive maintenance.
Yes,
So,
you are correct. Yes.
yes. Okay. So I wanted to know if these vibration signatures can be used for prescriptive maintenance as well. That is, in addition to diagnosing the bearing defect, if you can make automatic recommendations as to what corrective actions you can take if there's a defect. That's the first part of my question, and I'm going to ask a second part. And the other question I have is about the reliability of your predictions. How many false alarms do you get, or how many predictions of failures, false alarms, how many predictions of failures do you get when, in truth and in fact, you tear down the piece of machinery and the bearing was in pretty good shape and you just expended money trying to maintain something? So those are my
Yeah.
questions.
Yeah, so that's very good questions. And thanks very much, April, for those questions. In terms of the prescriptive diagnostics, there are many technologies, many manufacturers with prescriptive capabilities, especially coming from the vibration spectrum, but it's also based on user input, user output. So at least you know the phrase garbage in, garbage out. If there's a pretty good system setup, it can give you automatic alerts in terms of going a step further. Okay, and PeakView Plus is one of those that goes a bit step further and properly diagnose that whether the fault is lubrication based or is it actual and defect based, and gives you recommendations to perform lubrication or actually have scheduling of bearing changeout. And there are many technologies out there, many manufacturers that have this machine learning, these prescriptive in these prescriptive technologies in place, and it's related to the vibration spectrum and the frequencies being seen. But as you mentioned, it has to be defined or configured properly with the correct information, the rotating speed of the equipment, the type of bearing and the bearing number, those types of information to actually be input into the system to get the prescriptive part of it out. For the second part of the question, I mean, I've seen many false where people call bearings too early. All right. And as I mentioned before, that time and money have been spent into bringing down equipment and going into the equipment to take out bearings. And when in fact the machines or the bearings were good, it all comes back to user knowledge, user experience in terms of two parts, in terms of vibration experience and the equipment that they are using, right? So it depends on the technology you are using. Some people have shock pulse, some people have peak view. Sometimes these are very early indications of bearing effects, right? And typically, if you are not properly trained or don't have the knowledge of these technologies, you could be trained and well in vibration, but sometimes the technologies that you are using sometimes might not be set up properly in terms of the filters, the configuration, and it gives you a early warning. All right, and sometimes people may make a judgment call on an early warning and have the equipment being brought offline. And as you mentioned before, that time and money have been spent, time, money, and materials have been spent into bringing us the equipment when there was a false indication, right? And I have seen that in the past. That I mean, it does happen. Yes.
So just to clarify, so you're saying your ability to correctly predict the bearing fall depends on how well you know the piece of equipment or the type of equipment that you're using all of your analysis techniques with.
Yeah.
Is that correct?
Yes. Yeah. So it's user knowledge of the equipment that you're actually using to collect the vibration, and also the user experience that's analyzing the data. I think both of that has a big influence in terms of making decision to call a bearing early or not. Yeah.
Okay.
That's based on my experience. Yes.
Thank you very much. Those are
Sure,
very
no
clear
problem.
answers.
Yeah.
Thanks, April. Thanks for that question. I see you have a next
Yeah.
question here.
So implementing a PDM schedule, how often should testing be conducted? Should testing be conducted on newly installed equipment? Yes. So typically, what are the stages of testing? If you get high into reliability, there should be a FAT or factory accepted testings that should be done prior to the equipment being shipped from a vendor or from a supplier. So it depends on the criticality of equipment. Some companies, some customers do have factory acceptance testing. So what they may request from the supplier or manufacturer that an FFT or a vibration survey be done prior to the equipment being shipped onto the customer site. All right. When it arrives at the customer site and all comes back down to knowledge for the shipment of equipment, sometimes manufacturers may disassemble sometimes and ship bearings separately. Sometimes they may lock the shaft of the equipment so there's no rotation during shipment to avoid any type of false brenneling. So when it's actually installed on the equipment on your facility, especially if it's a driver piece of equipment, if it's a motor turbine, steam turbine, gas turbine, it has to do an unload or uncouple test, right? So that's the next step to unload or a solar run to ensure how the vibration is before it has been coupled. If that's has been done and everything is okay, because you're trying to ensure that there are no defects. And I have seen equipment come straight from manufacturer that they add defects from shipment, all right? And we are all, I think now we are being plagued with inferior manufacturing, or there are manufacturers falsely advertising high brands, but really cheap manufacturing material techniques, and they avoid their castings, their defects. So after the no load or solar on an equipment is coupled, you do a loaded test to ensure there are no issues. Once that is in place, basic place to start with a PDM program is monthly. All right. So once you start with a monthly program for a PDM type of data collection, if there's no increase in vibration or defect frequencies, you can maybe move that. Well, you can maintain your 1 month, but as you start to get bad actors where you have high vibration, you may want to move it from a monthly to maybe a fortnightly or 2 weeks. All right. And if the bad actors keep behaving bad, you know, to bring that a weekly schedule, or sometimes we have daily schedules, data collection depends on the defect, right? So it depends on your situation that the PDM schedule, right? So there's a next question. How can you properly capture a bearing defect using peak view analysis? Right. So peak view is one technology that's patented to Emerson. So Emerson has peak view technology. How it works in terms of proper capture of bearing effects, right? So ideally, those who are involved in vibration, the ideal way is to have your accelerometers, what is known as stud mounted, or actually drilled and tap into the bearing housing at the load zone to ensure there's good transmissibility of data. All right, but typically that is not the case available for practical reasons, safety reasons, accessibility. So what you may have is your accelerometer. Sometimes we may use a two-pole magnet or a flat-pole magnet. But once there's a good transmissibility from the bearing housing to the sensor, all right? So once the accelerometer measures that vibration data, and you have that technology from Emerson for peak view, once you have the proper filters in place, the peak view spectrum or waveform will give you the bearing effect frequencies. So it all depends on if you have proper connectivity or connection to the bearing housing, if you have good accelerometers, and if you have the Emerson technology for peak view, and then there's peak view plus, which goes a step further to distinguish if it's lubrication or if it's mechanically related. So I hope that answers your questions, Joshua.
Yeah, thank you, Aaron. Thank you, Joshua, for your questions. I see one person who had raised their hand earlier. I see it not raised again. I believe it was Goldie. I'm not sure if they're still willing to ask a question.
Good evening, everyone. Rishi, good evening.
Hi, good evening. How are you?
Okay, fine, thank you. And yourself?
Good, good.
All right. I just wanted you to just call it back for me, please, the four major components of bearing analysis. The first one is the four major components, the four defect frequencies, and what are the other two?
Right. So the four major components, right? So it would be inner race, outer race, the element, and the cage.
Right.
The other one will be the defect frequencies. So
Right.
it will be the defect frequencies associated with those parts of the bearings, right?
Mhm.
So you'll have a defect frequency of the inner race, outer race, the element, and the cage. And then there are the four stages of bearing failures: stage 1, stage 2, stage 3, and stage 4.
Okay, thank you.
No problem.
Thank you.
Somebody
Goldie.
had, yeah.
Yoquin, you could go ahead.
Hi, good night, blessings to everyone. Hi,
Good night,
Rishi.
good night. Hi, good night.
I'm a machinist, right? And earlier in the presentation, in your description, you mentioned about the interference fits on the shafts, on the housings that these bearings fit, right?
Yeah.
My question is, can it be determined through vibration analysis that an issue, can be traced to the incorrect interference fit of a bearing? Let's
Yeah.
just say we have a motor and the end shields where the bearings will be either pristine or chilled and inserted. If
Yeah.
the interference fit is too much,
Yeah.
can with the vibration analysis pinpoint that so that you wouldn't have to go all the way to scrap down and then measure to see, where the interference fit is off? Can that be determined?
Yeah. So that can be determined with regular vibration. So, and also with the bearing type vibration analysis. So if there are too much clearances, right, sometimes they get mechanical looseness, right? So typically in mechanical looseness, what they will look at is what is known as a 1x vibration with harmonics. So that kind of guides you, indicates you that there are too much clearances happening in your bearing housing. So it tells you there's a lot of looseness happening. So that is known as mechanical looseness. Sometimes if the bearing is loose in the housing itself, it actually generates a frequency a little less sometimes than the runner speed. So yes, vibration can be used to diagnose if there's too much of clearances or there's too much or tight fits. So sometimes if there's tight fits, it'll actually be pressing into the bearing and actually causing uh, a high spike of those same defect frequencies, especially the outer race, right? So if it's actually too much of clearances causing pressing into the bearing, those frequencies shows up and shows up very strong, and the vibration can guide you. Yes, there's some issues with the tolerance fits. Yeah. I hope
All
that
right.
answers
Thank,
answers the
yeah,
question.
thank you. Yeah, it does.
Yeah.
I just wanted an understanding. Thank you.
So vibration can guide you on majority of mechanical and electrical faults prior to actually having any kind of intervention into the equipment. So it's a pretty good technology, not only for bearings, but misalignment, mechanical looseness, unbalance, cavitation, impeller default. So it's widely used as a good technology. I saw there was a next question, Christopher.
Yeah. Thanks, Yoquin. Aaron again, right? He asks, depending on the situation, in an emergency, bearings may be replaced on site. What tools would you recommend to be used for proper removal and installation of the bearing?
Right. So there are bearing removal tools, special tools used for actually removing bearings from shafts and IDs or bearing housings. All right. So there are special grabbers or claws you could use to actually remove those bearings from the shaft or from the internal housing. All right. For installation, there are bearing heaters. All right. There are many manufacturers of bearing heaters where you actually place the bearing into the heater, rotate, and actually gives you an even distribution of heat onto the bearing to actually expand, to have interference fit, as the guy mentioned before. So there are a lot of tools widely used. Also depends on, I've seen a lot of people try to use hammers and stuff like actually pounding the bearing into place, but good maintenance or installation practices guides or dictates the reliability of the equipment moving forward, and proper procedures, proper guidance in terms of the procedure, the tools, equipment for extraction and installation is what is important to avoid those effects, right? So there are bearing pullers, there are bearing heaters that can be used for heating to have proper insulation and those interclearance fits. But it's also good, as the guy mentioned before, to actually mic your bearings, mic your housings to ensure that they have the proper clearances you need before actual installation. Sometimes you may need to build back up a shaft or build back up a bearing housing because after time they may be wear. So just don't take full face values that clearances are okay and just swap in, swap out. Always mic back your housing and the shafts and the ID, OD, and make sure that they are set for tolerances.
Thanks, Aaron. Thanks for your question again.
Yeah,
I
I
see,
hope that
let's
answers the question.
I see Leston ask a question here on behalf of the non-vibration guys, right? What techniques can be used to access, well, I guess he meant assess bearing health.
Assessment.
Yeah. Mhm. Use
Oh,
the
okay. Yeah, so there are many techniques that can be used. Ultrasound is one. So ultrasound, especially if it's in the earlier stages of bearing detection, ultrasound can be used for bearing detection to bearing health. Lube oil or lubrication analysis. So if there's lube oil sampling analysis, if there's grease sampling analysis, that can also be used for detection. There are vibration measurements. We mentioned the vibration measurements. Very high frequency detection techniques. We mentioned those high frequency detection techniques, peak view, shock pulse monitoring, spike energy. There's also high frequency detection. There's also enveloping or horizontal amplitude or demodulation. Those techniques can be used. Vibration spectrum can be used. Vibration time waveform can be used. And there's autocorrelation of the time waveform, and there's circular plots of the time waveform that can be used. So those are some of the techniques that can be used for assessing bearing health. Temperature is one, but temperature is also at the latter stages of failure. The time temperature has been detected, it might be a bit too late in stages of bearing failure. So infrared or temperature can be used, but it's further down in terms of time for failure.
All right, thanks a lot. I guess I would ask a question on behalf of some of you guys to I know you mentioned the ball pass frequency of the inner race, and you showed the sidebands, right?
Yeah,
yeah. Well, as a defect, are there sidebands for some of the other defects as well that you mentioned, or?
Yeah. So in terms of the ball spin effects, so in terms of the actual element, if it's a ball element or roller element, that also produces or has a sideband of the cage. So whatever, so sometimes there's be a cage or a thing that is actually holding those elements together and actually modulates those elements being rotated. So it'll have sidebands of the train or FTF frequency around those ball pass or ball spin defect frequencies. Yeah.
Right. I see you Quinn have a question here.
Okay, so how well do you do this one? So do we need to modify this time during the
Yeah, you could go ahead, Quinn.
All right. Rishi, again,
yeah.
so I recently had a team. I also work offshore, and I recently had a team come on site to do quarterly vibration checks on our rotating equipment.
Yeah.
And in some of the equipment now, they hooked up their sensors where, didn't have any bearings at all, certain parts of it. And in other equipment, there wasn't bearing, there was bushing.
Bushing, yeah.
So would still collecting data in those areas impact the reporting significantly?
In terms of it would it be useful in terms of effective? If that was yeah.
Or
So
will it show off the readings at all or anything like that?
No. So in terms of if you have bushing, especially long pumps, multi-stage pumps, clear well pumps, submersible pumps, sometimes these equipment have bushings installed instead of bearings. Vibration measurements can be helpful, yes, to guide you in terms of if clearances are being opened up and you come back to the same mechanical looseness. So if there are bushings as compared to element bearings, yes, vibration can have or will provide value to you. Yeah.
Thank you.
Yeah, thanks, Quinn. I see Vishana have a question here. A long question, I will read it out, right? All right. Manufacturers gives tolerances for their bearings, and some, if not all, also include corresponding tolerances for the housing and shaft. From your experience, how well do these tolerances hold up? Do you need to modify it most of the times, or is it satisfactory most of the times? How do you know if there's an issue with the tolerances, since some of these tolerances will be in the 1,000th of an inch?
Yeah. So TOWs, so most of the times manufacturers tolerances are pretty good to be used. All right, their guidelines are some are pretty good to be used. What if there are any changes to be made or if there's any differences will come over time, but where? So manufacturing tolerances, yes, always refer to OEM guidelines, especially for new equipment. So OEM guidelines, yes, they are pretty good in terms of tolerances, float, axial truss, bearing clearances. So these are very good guidelines to be used. And then after time, sometimes wear may happen and clearances may open back up, and you may have to revert back to what the OEM recommended for clearances. So sometimes it may be required to have build up or build over shafts or build back up bearing housing clearances. So always go what the OEM recommends because most of the times they are pretty accurate in terms of tau, sometimes 1 tau, sometimes 2 tau, 3 tau, if it's ID tau D or if it's float. So I best guess, yes, these tolerances do hold up.
Yeah. And I guess that, to answer the last part of the question, they asked if there are any issues with these tolerances, or how do you know now if there are issues with these tolerances? I guess he meant like vibration wise now. And
Yeah,
one notice is sometimes you use so many high frequency techniques and you tend to see harmonics of the 1x vibration now.
yeah,
In some of the early stage detection techniques, right? So those
Yeah.
are some of the things that might give you an indicator that some of the tolerances may be slightly compromised in the inception stage, you know. Yoquin, again, you have a next question. Go ahead, Yoquin.
It's not really a question, it's just a contribution to Rishi's
Yeah, sure.
answer for the
Yeah.
last question. As a machinist, once you stick with the tolerances, as they correctly said, Rishi, it'll be fine. Now, the challenge we have in some instances, let's say the clearance is too much, and sometimes like for suction centrifugal pumps, it's not applicable to fill back the area and machine it. We'll have to, undercut it and replace it with a wearing. And that wearing will tend to be another material than the material for the pump itself. So in a scenario like that now, the clearance, the recommended clearance will have to be adjusted because of the nature of the material that we're using as wearing, right? In order to give us certain reliability. But
Yeah,
once you stick with the tolerance, generally you come out well. You come out on point
Yeah.
because that's calculated.
Yep. Sure. Somebody has raised their hand this now.
Yeah,
Yeah,
Mustaq.
Mustaq. Yeah. Good
Yeah.
night.
Yes,
Good night, all.
good night.
Right.
Good night.
My question is, with regards to force Brennan, right? When you have a main and a standby, say a centrifugal pump, and they say probably around 3 feet apart, we see a lot of false Brennan with that. What do you advise in a case like that? Because sometimes you replace a bearing and the cycle time for the standby pump wouldn't be until a month after.
Yeah.
So you will always go back on that when you're trying to get baseline data, and then probably
Yeah.
a few weeks after you don't see very high values on your FFT curve already.
Yeah. And it was down all the time, right?
Correct. That's correct. Yeah.
Yeah. So I mentioned, so one way to start is the rotation cycle. So if your rotation cycle cannot be achieved, because sometimes if you say yours is a month or every 2 weeks, that rotation between the standby and the primary or A and B, there's also, you have to look at what's known as isolation. All right. So isolation in terms of isolation mounts or dampening to avoid transmissibility of vibration from one equipment to the other. Typically, it's typical arrangements. If it's pumps, sometimes they are both connected via the same piping, if it's the same suction piping. All right, they may have to actually have isolation of vibration being transferred from one equipment to the other. So there are vibration isolators that can be installed to avoid transmissibility of vibration from one equipment to the other. You'll have to look at that as an option if it's a keep reoccurring happening to actually get to the root cause of it. So if the schedule can be changed for the rotation between standby and auxiliary or the A and the B, then you could look at isolation dampeners or isolators or even the piping to avoid. Most of the time, sometimes they transfer through if it's a steel foundation, through the floor, concrete, or through connected or mutual common piping.
Great. So actually, that's part of what I found that when I'm finishing up a thesis. And one of the root cause I found that they really wasn't paying attention was that false Brennan that was happening all the time. And they had repeated failures in a short space of time. And that vibration isolation you're speaking about, that was one of my recommendations. So I'm glad you confirmed that.
Yeah.
So,
And
thanks.
there are many tests you could do. You could have one accelerometer on the equipment that is running, and then another accelerometer on the standby equipment that's not running. And there are many tests you could do, transmissibility tests, you could do coherence, you could do phase checks, and they can actually see if the frequencies that happening on the standby equipment is related to the or be transferred from the running equipment. If you know what is the main frequency of concern, you'll have to get isolators designed to that frequency to avoid to make sure the isolators operate in the isolation range, right? So manufacturers of the isolators will give you the graph for those isolators to ensure proper isolation. Piping, a lot of transmissibility happens in piping. Some people don't understand that, but the very common cause or pathway for transmissibility of vibration through the piping, connected piping, also connected skids and foundations. So if we're looking at the isolators, ensure it isolates the correct frequencies. All right.
Thanks so much.
Yeah.
Thank you, Mustak. Okay, so I think that should be enough questions for tonight. I think Rishi did a good job in answering your questions. So and I know that you know, they get a lot from this presentation. They give them a lot to think about, and
Yeah.
And for those who had to apply any condition monitoring program, I hope that the information that Rishi shared, you could take it to your plant and put it into practice. Right. Let me see. Before we go, I see Mustak, you have one more question?
Yeah, one
before we
thing I
go?
just wanna
Yeah,
so
go ahead.
I agree with you with regards to this information that you shared tonight, because I wish I could really take notes here. I know it recorded, but can we be
Yeah.
able to get this information that you shared with us tonight, like the
Yeah,
recording, to see?
Yeah, I believe the recordings are Christopher Weston or I think they could speak more on that.
All right, thanks.
Yeah.
Yeah, Mustak, I'll talk to I guess I'll talk to Leston about it and see what we could do to if we could able to get it out and get back to you. Right?
Hi, good night. Hi, everyone. Hearing me, right?
Yeah, understand. Yeah. Good night.
Yeah. Hi, good night. Yes, the recording I could, because it's being saved, so I could get it out to the mechanical public after after tonight. That wouldn't be a problem. So
Okay,
yes.
that's great. Yeah.
I appreciate it. Thanks a lot.
Yeah, no problem. Thanks a lot,
Okay,
Rishi.
yeah, thanks, Leston.
Yeah.
Tobias,
I will see. I will see about the PowerPoint, right? So
yeah.
Tobias, I will see. But typically, if you, I mean, there are a lot of free information out there. YouTube, mobile sites. I mean, I think a lot of free information in vibration. You can get that. I mean, a lot of way. But I mean, I'll see if I can what I could do with the PowerPoint. I will try my best, Tobias.
Okay. Thanks a lot, Rishi.
Yeah, no problems.
Mustak, next.
Yeah, and
Question?
just to respond to Rishi, it's not so much of your PowerPoint, because a lot of these things are right about that. We could get that online,
Yeah.
because most of these the values that they're looking for on the FFT curve, they have formulas. I did analyst level 1 and 2 with Update International, so I have a fair idea how these things work, and they have formulas. You just plug in your data and you get to see exactly where these FFT values fall.
Yeah.
But you see your responses in terms of troubleshooting, you don't get that outside as much, and you have a lot of skill I see already with this. So
Yeah.
this is where we need to, piggyback on and use that in industries, and which is really appreciable right now. So thanks so much.
No problem, sir.
Yeah, thanks, Mustak. Rishi, is Imani your way?
Yeah. No, I just here to share my knowledge because I mean, we're all here to help and share one another in this industry, and it all ties back to safety. And I mean, that's how I look at it, because once the equipment is not reliable, it's not safe. And I don't feel safe and comfortable with people walking around unreliable equipment. It really is a safety issue. And I
Thanks,
wish everybody could see that and drive that at their facility.
Thanks, Ushi. Agreed. We appreciate that, and
Yeah.
we appreciate the time that you take for this presentation, and
Yeah, no problem.
I impart to everyone. With that being said, I would like to close and wish everyone a good night and stay safe. Thanks, everyone.
Take care. Good night, everyone.
Thank you.
Thank you.
Thanks a
Take
lot.
care.
Take care.
Bye.